Hi everyone, I'm Nathan. I'm a mechanical engineering major here at OSU, and this is going to be my second year on the underwater robotics team. In this video, I'm going to walk you through the basics of 3D printing, so that way you'll know how you can apply 3D printing to your own projects on the team. So there are three main sections to this video. There will be timestamps linked in the description for the specific sections. So in the first section, we will learn how to design a part for 3D printing. Then we'll go over how to pick the correct material for your application. Finally, we'll learn how to convert a SOLIDWORKS part into an STL file so it can be sent off and printed. In this section, we will cover how to design a part for 3D printing. Now, to get the best results from a 3D printer, parts need to be designed with the 3D printing process in mind. As a note, this video is only referencing FDM 3D printing, which is the process that works by melting plastic with a nozzle and laying down thin layers of molten plastic on top of each other to build up a part, which can be seen in this image. Because of this printing process, there are a few considerations that need to be made for any part to be 3D printed. The first consequence is that the bonds between the layers is only about 40% the strength of the plastic itself, which can be a weak point for the part. Secondly, 3D printing was developed after Isaac Newton, so the molten plastic unfortunately can't defy gravity. This means that any steep overhangs or floating parts would need to be supported from below to prevent the layers from drooping down due to gravity. You can see in the image what this T would look like if supports weren't used. Lastly, these printers are fairly accurate but still have some inconsistencies. And parts will have small staircases on them because of the layers, as can be seen in the image on the right. I mentioned how the bonds between the layers are significantly weaker than the plastic itself, so let's learn how we can design our parts to avoid this issue. The orientation a part is printed in determines what direction the layers go, so you can use this to make the layers go in a direction so the forces would not be trying to pull apart or shear the layers. This image shows a good example. In the first case, the force that is acting on the part is trying to shear the layers apart, so it will likely break without much effort. The second part is oriented so the layers will not be pulled apart or sheared by the force, so it will require a much greater force before the part fails. I will soon be covering how the orientation of a part can also be used to reduce the amount of support material needed, but it is very important to note that the orientation of a part should be made to withstand the forces first as the top priority. It is better to have a part that works and was printed with supports than a part that had no supports and breaks. This image here shows some good examples where 3D prints are weak and strong with various forces. You should use this as a reference when designing parts. When forces are pulling the layers apart, the part is weak. When forces are compressing the layers, the part is strong. When the forces are pulling along the layers, the part is also strong. But when the forces are shearing the layers, the part is weak. So make sure you understand what forces your part will experience and the orientation that will be the strongest for those forces when designing. Next, we will cover supports. So supports add time, material, can be difficult to remove, leave a poor surface finish to the area they were supporting. To avoid these negative aspects, they should try and be minimized wherever possible. There are a few techniques that can be used to minimize the amount of supports. The first technique is by changing a part's orientation. The image of the T on the right shows how different ways of printing the part need different places supported by the green lines, and the final orientation needs no supports, which would be ideal. So when designing, pick an orientation that will minimize the overhangs. The next technique is to add chamfers to turn overhangs into 45-degree angles. 3D printers can comfortably print angled surfaces if they are less than 45 degrees. As you can see in the image, the part with the chamfer eliminates the need for supports. Now, it's not a huge deal if you can't make your part supportless, but try and implement these techniques wherever possible. The last design consideration that I'll be covering is adding clearances to your part to the spots where it interacts with other parts. I mentioned how 3D printers aren't perfect, and this would be why if you have a 1-inch hole and a 1-inch diameter rod, they wouldn't fit together. To make them fit, a small gap would need to be modeled in to account for the imprecision printers have. This step may not seem like a big deal, but it can save you hours of sanding a part down to size if done correctly. It is important to note that the amount of clearances needed varies between printers, but I'll give you a starting point. So let's say you want two parts to press into each other and you want it to be very difficult to remove the parts afterwards. You should add an offset of around 0.1 millimeters to all surfaces that interact. And I wouldn't recommend going lower than 0.05 millimeters if you want it to be tighter. However, if you want a part to press into another part and stay in place, but you can still move it around with some force, I'd recommend an offset between 0.1 to 0.25 millimeters. And let's say you want two parts to slide past each other with minimal friction, you should add an offset at or above 0.25 millimeters. Use this chart as a starting point and iterate from there. If you have a really big part or having to reprint it to adjust clearances would be timely or costly, consider making a small test print like the one shown here. It has a shaft with holes that have different offsets that can be used to test clearances on a small print before applying those clearances on a larger print. Congrats! Now you know the basics of designing a part for 3D printing. If you're confused, have questions, or need help, don't be afraid to ask me or any one of the team members. We'd be happy to help. Now in this next section, we will cover how to choose the correct material for your 3D print. 3D printing materials comes as a round plastic filament on a spool that looks like this. There are different types of plastic filaments that can be made, and each has its own benefits and drawbacks based on the type of plastic. This chart here covers the materials that will be suitable for most applications. The first is PLA. This is the most common 3D printing material, and for good reason. It prints easily and has excellent strength and rigidity. It is a great choice for over 90% of applications, I'd say. However, it has two notable drawbacks. First, due to its rigidity, it is not great at absorbing sudden impacts, which would cause it to shatter. So if a part would take repeated impacts like drone landing legs, it wouldn't be the best material. Its other drawback is it will start to get soft and deform under mildly low temperatures. So if you want a part to mount hot electronics or sit inside a car in the middle of a summer, it wouldn't hold up well. The next two materials are PETG and ABS. For reference, PETG is the plastic soda bottles are made out of, and ABS is the plastic Legos are made out of. They are fairly similar materials and can cover some drawbacks of PLA. Both are slightly more flexible, which means they can take more of an impact than PLA but sacrifice some strength. They also deform at a higher temperature than PLA, with ABS's being the highest. However, ABS can be quite difficult to print, so I'd advise choosing PETG for a better print result in most circumstances instead of ABS. The last material I will cover is TPU. It is a flexible, rubber-like material that could be useful for something that needs to be grippy or something that needs to be able to bend. There are other fancier materials out there, but this table should help you decide the best material for your application. For the final section, I'll walk you through how to convert your SOLIDWORKS part file into an STL file. First, what the haze is an STL in the first place? Well, it is simply a file that represents a 3D model with a bunch of triangles. You can see this dolphin here has been subdivided into triangles to approximate the shape of the animal. This file is important because it's needed to print your part. Open up your desired SOLIDWORKS file and go to File, Save As, and give it a descriptive file name. On the Save As Type dropdown, select STL near the bottom. Then hit the Options button. This screen is where the settings of the STL can be set. Click Custom under Resolution and slide the deviation and angle sliders about 3/4 of the way to the right. This is how you adjust how fine the triangles are for the model. Ensure the units are set to millimeters in the top right. Click OK and click Save. Now that you have your STL file, Send it to the person that will be printing your part, along with any notes about the material, print orientation, and functionality of the part. Congrats, you learned how to design a part for 3D printing, select the right material, and how to save a part as an STL. If you have questions or need help with any of the aspects of 3D printing, I'd be happy to help. Thanks.